we're going to take a look at a few more examples of solving trigonometric types of equations that have higher order than 1 or degrees of higher than 1. And remember, when we're finding these, we're going to find the solutions from 0 to 2 pi. All right, so we have this equation, 3 cotangent square of x over 7 minus 1 equals 0. So let's start by solving this for the cotangent square function. Okay, so I'm just going to add 1 to both sides. So I get 3 cotangent square of x over 7 equals 1. I'm going to divide by 3. So cotangent square of x over 7 equals 1/3. And then the last thing I'm going to do is I'm going to take the reciprocal of both sides because I don't like the cotangent function. So I'm going to take the reciprocal. Notice when I take the reciprocal, I do not take the reciprocal of what's inside the interior angle, the double angle or the multiple angle, excuse me. So this is going to be the tangent square. We leave the x over 7 alone, and the reciprocal of 1/3 is 3. Okay. Now we're going to take the square root of both sides. Okay, and remember, anytime we take a square root of both sides, that means that we might have some extraneous solutions. Okay, we might not, but we might. And so we're going to end up with the tangent of x over 7 is going to be equal to plus or minus the square root of 3. All right. Now, remember, plus or minus means that we're going to be in all the quadrants. Okay, so we don't have to worry about our all students take calculus. Okay, and so we're looking for when does the tangent of x equal the square root of 3? Okay, so that's the question that we want to really answer. And that's going to be at pi thirds. Okay, we should have that memorized. Okay, if you remember one of the earlier videos in this section, we had that table. And so we're going to take the x over 7, and that's going to be equal to pi thirds. But we can't forget that we need all the reference angles of pi thirds in all 4 of the quadrants. Now, one thing that I always tell students is if you want your reference angles, okay, and you don't want to compute them, just go in the unit circle and look for anything with a denominator of 3. Okay, so in this case, we have 2 pi thirds, and then 4 pi thirds, and then 5 pi thirds. Okay, so we have 2 pi over 3, we have 4 pi over 3, and we have 7 pi, or 5 pi. Sorry, I was thinking about that 7 on the left-hand side. So we have 4 pi over 3 and 5 pi over 3. All right. Now, we're going to multiply both sides by 7 to clear this denominator out. Okay. And so we end up with 7 pi over 3, 14 pi over 3 by multiplying by 7. And then 28 pi over 3, and then 35 pi over 3. Okay, so those would be our solutions. But remember that we want solutions that are between 0 and 2 pi. Okay, and remember 2 pi can be written, if we wanted a common denominator of 3, as 6 pi. So anything bigger than 6 pi is not going to be in the domain. This is not, this is not, this is not, and this is not in the domain because these are all bigger than 6 pi thirds. Okay, so they're all bigger. So in this case, there's no solution. All right, and how can we check that? Well, what we can do is we can just go ahead and graph tangent of x over 7 and then the square root of 3. Okay, or tan square of x over 7 and square root of 3, and we could see whether or not that produces our solutions. Okay, so it's going to be our tan of x over 7. All right, and we want to see where that equals either positive square root of 3, okay, or negative square root of 3, or positive square root of 3. Okay, and I want you to notice that the only place that it even comes close is up here at 7 pi thirds, which is well beyond our 2 pi. Okay, so unfortunately, there is no solution to it, at least in this interval. Okay, there are an infinite number of solutions, just not in a given interval. All right, now a couple more types. We're going to have to do a little bit of factoring with these. Okay, and I'm going to show you the technique for this. Remember, anytime that you start with a square, set it equal to 0. Do not divide by sign in this case, okay? So I'm going to subtract sine from both sides, and I'm going to set this up as 2 sine square of theta minus sine of theta minus 1 equals 0. Right? Now, let's think of sine of theta as x. And so sine square of theta would be x squared, right? So what I'd like to do is I'd like to write it as just a polynomial equation. Okay, so I'm going to write this as 2x squared minus x minus 1 equals 0. And notice that we can factor this trinomial. Okay, so it's a nice, easy trinomial to factor. So we have a 2x and an x. To get to negative 1, I'm going to put minus 1 and plus 1 here. And remember, if you want to check that, you could just FOIL it back out. Okay, and so what I could do is I could replace x with the sine function. Okay, and so this expression, 2 sine squared minus sine theta minus 1 equals 0, can be written as the quantity of 2 sine of theta plus 1 times the quantity of sine of theta minus 1 equals 0. Now, of course, if you don't trust that, what you can do is you can FOIL that back out. All right. And if you FOIL it, what you'll clearly see is that you get back to this. All right. So now I'm going to set both of these factors equal to 0. Okay. So I'm going to have 2 sine of theta plus 1 equals 0. And then sine of theta minus 1 equals 0. And I'm going to solve those two equations. I end up with sine of theta equals negative 1/2 by subtracting 1 and dividing by 2. And then I get sine of theta equals 1. And what I'm going to do is I'm going to go into the unit circle, and I'm going to look for where the y coordinate is equal to negative 1/2 and where the y coordinate is equal to 1. And so in our unit circle, the y coordinate is negative 1/2 at 7 pi 6 and also at 11 pi 6. And then we also need to know where the sine is equal to 1, and that's going to be at pi halves. So our three solutions are 7 pi 6, 11 pi 6, and pi halves. Okay. Now, of course, if we don't trust this, what we could do is we could just plot this and see what the graph looks like, and then see where it crosses the x-axis. Okay, so let's just do that just to verify. Right? So we have our 2 sine square, and so I just put sine of x and square it, right? And then we needed a minus sine of theta. Right, so in our calculator, we have minus sine of x, and then minus 1. And then we don't need these, right? And so if we look, we have pi halves. And remember, the other two solutions were 7 pi halves, or 7 pi 6, excuse me, and 11 pi 6. Okay, so notice that that's what our three solutions were. Okay, so nice and easy for us to be able to solve. Okay. One last example that's sort of similar to that, we have a secant square of x plus secant of x equals 2. Let's start by setting the equation equal to 0 by subtracting 2 from both sides. And so I get the secant square of x plus the secant of x minus 2 is equal to 0. Let's think of secant as x. And what I'm going to do is I'm going to rewrite this as a polynomial equation. So I have x squared minus x minus, or x squared plus x minus 2 equals 0. And now I'm going to factor this. To factor it, I can write this as x plus 2, x minus 1. And of course, if you don't trust your factorization, FOIL it back out, and you'll see that it does FOIL back out to the original polynomial. And so I'm going to replace this x with a secant of x. Okay, so now I'm going to factor this into secant of x plus 2, secant of x minus 1 are both going to be equal to 0. Now I'm going to set both of these factors to 0 by the zero factor theorem. So we have our secant of x plus 2 equals 0, secant of x minus 1 equals 0. Now I'm going to solve those two more simplistic equations. I'm going to subtract 2 from both sides of this first equation, and I'm going to add 1 to both sides of the second equation. We don't like secants or cosecants or cotangents as much as we like sines, cosines, and tangents. So let's take the reciprocal of both of these equations to put it in terms of cosine. Because remember, the reciprocal of secant is cosine. So we're going to get the cos of x equals negative 1/2. And we're going to get the cos of x is equal to 1. All right, since the reciprocal of -2 is -1/2, the reciprocal of 1 is 1. Finally, we can just figure out on our unit circle, where is the x coordinate equal to 1/2, and where is the x coordinate equal to 1? Okay, because remember the cosine represents on the unit circle the x coordinate. And so we go to -1/2, or we try to find all the -1/2s. There's one at 7 pi, or sorry, there's one at 4 pi thirds. There's one at 5 pi, or there's one at 4 pi thirds. There's one at 2 pi thirds for the x coordinate. Okay, so we have 2 pi over 3, 4 pi over 3. And the cosine, which is the x coordinate, is going to be 1 at 0. Okay, so we go over here, right here, we have these three values. Okay, if we wanted to, we could go ahead and just verify this. Okay, so last thing we're going to do is we are going to go ahead and just simplify by putting this into our graph. All right, and we have our secant square. So I'm just going to rewrite this as secant square. And then I'm going to write this as a plus secant of x. So I'm just writing this in here. So plus secant of x. And then minus 2. And then that was equal to 0. And so notice right here is 1 point at 2 pi thirds. Okay, so we go to our solutions, 2 pi thirds, and then we have 4 pi thirds as another solution on our graph. We also have 0. This guy right here is 2 pi, but remember, we don't want to include that because that's actually coterminal to 0. Okay, so that's a way that we can check this to make sure that we're good. All right, so that's all like the higher order types of trigonometric equations. Okay, so we have one last video, and we're going to take a look at what happens when we need our substitutions by using our formulas. So remember, we had a lot of trigonometric identities in previous sections, so we're going to use these in the next videos.